ID, the Future, a podcast about evolution and intelligent design.
How did life begin? Chemical evolution would have required a continuous supply of energy to create the first life. But are the energy sources that have been proposed for chemical evolution realistic? Hello, I'm Eric Anderson, and on this episode of ID the Future, we're joined by Dr. Robert Stadler to help us explore some of the challenges chemical evolution would have faced in order to harness the energy needed to originate the first life. Stadler received a degree in biomedical engineering from Case Western Reserve University, a master's in electrical engineering from MIT, and a PhD in medical engineering from the Harvard-MIT Division of Health Sciences and Technology. He has worked in the medical device industry for more than 20 years, has over 140 patents, and is co-author of the recent book, The Stairway to Life, An Origin of Life Reality Check. Thanks for being back on the show with us, Rob.
Hey, thank you, Eric. It's always a pleasure to discuss the origin of life with you.
Yeah, awesome topic. One of my favorites as well. So, Rob, you've been involved in a wonderful new video series on the Discovery Science YouTube channel called Long Story Short. Just briefly tell us a little bit about this series.
Yeah, it's been a great experience. We got together, there's a group of 5 scientists, chemistry, biochemistry, geology, and as you mentioned, more of a medical engineering side on my part. And we got together with the goal of making this very approachable and make it also kind of fun and get it through on YouTube so anybody could watch it anytime. And part of that is, different media attracts different people, of course. And I think the old-fashioned way of picking up a book and spending hours reading it seems less attractive in today's world than popping up a video. So that's what kind of drove it.
And this is what, the 3rd or 4th video on the origin of life?
Yeah, this would be the 4th in the series.
There was one, I think, about the basic building blocks of life, one on biopolymers, and one on membranes. Tell us what this new video is about.
Yeah, this one is all about energy harnessing. And that's a term you don't hear so much. How do you harness energy? And I think it's largely unappreciated because you'll hear origin of life researchers and certainly science popularizers that will speak in terms of there was plenty of raw energy there on the prebiotic Earth. You got volcanoes and lightning strikes and radiation and even meteor impacts and the sun. And so there's plenty of raw energy to get life going, in their opinion. But I really don't think they understand the delicate balance you have to have that all those forms of energy can be just as destructive, in fact, predominantly destructive, rather than being constructive to build complicated molecules and organize them and add information, of course, and have homeostasis. All of that requires a very particular kind of energy delivered at just the right time and the right format. And that's what they're missing.
Okay, so talk to us a little bit about that. To operate a cell, you got plenty of energy on the Earth. So the question is, well, I think there's a couple of things, right? One is the diffusion, and you mentioned this in your video at one point. In other words, how diffuse is the energy? How focused is it? And more importantly, there's the question of how the energy gets harnessed, right? And in the video, you guys talked particularly about the machinery of life.
Yeah, so as we mentioned, there's all this raw energy out there in a prebiotic Earth. And the argument we have is that it can be more destructive than constructive. And there's plenty of practical examples in your own life. I mean, you can have an earthquake that shakes up your house, but no one expects that earthquake to organize the materials on your desk or to match up your socks from the laundry basket, right? It doesn't, there's a lot more destruction that goes on, obviously, than construction. And you could say that for any kind of these raw energy sources of lightning or volcanoes or even the sun can, of course, be more destructive than constructive. And so in order to take that kind of raw energy and make some good use of it, you need a complicated machinery that's going to convert it to exactly the right form and even have it be stored conveniently and be ready just when you need it, kind of just-in-time use of the right kind of energy at the right time in the right place. And life does that all through life, all of life. And prebiotic Earth doesn't do that and doesn't provide that. That's the fundamental challenge here.
Yeah, this is a really good point, because I think as most of us go out and walk around the neighborhood or go on a hike, We see all these animals and plants that are harnessing energy, and we kind of have this naive impression, don't we, Rob, that it must be easy. This energy is coming in from the sun and ta-da.
That's right.
But what you're pointing out is that the energy has to be channeled in a way that's productive for what the cell is doing or what the organism is doing. You don't just put energy in and get a cell out the other side.
Yeah, and it has to be exquisitely constructive, actually. If you're going to reproduce your DNA, let's say your DNA is a million base pairs, you have to produce it basically exactly, right? And if the energy gets out of control and starts to break bonds, even if an electron gets loose and just, makes free radicals and starts blowing things up, crashing into things and causing chaos, you'll never get something as exquisitely precise as a million base pairs of DNA all lined up perfectly.
Right. So to get a specific result, you have to have a specific setup that's geared toward putting that energy to useful work. One of the examples I like to use is that if you take a can of gasoline and pour it on your car and set a match to it, that's not going to be very constructive. So merely applying lots of raw energy to a system isn't what's needed. On the other hand, if you have this carefully organized, precise set of machines and controls, you have the gas tank where you store the gas, the appropriate tubes that get the gas where it needs to go, the right mixture of gas and oxygen in the right chamber with the right type of mechanical systems around it, such as the pistons and crankshaft. If you have all that together in a coherent and organized way, then you can take that can of gas, take that energy, and use it a little bit at a time in the right way at the right moment to do what you need to do and drive your car.
Exactly. So it's that complex set of machinery that's clearly built for a purpose, that's able to take raw energy and make good out of it. And I can't think of an example where you can get lucky with raw energy that's going to get you very far. You might be able to prove one step in a direction, but then it'll all blow up and take you back 12 steps.
Good point. I like that. So the Miller-Urey experiment is something that most of our listeners will be familiar with back in the 1950s. And, they produced some amino acids from this experiment that they set up. Basically just ran an electric spark for a period of time and produced some amino acids. Why would this not be a good precursor in the context of energy? We've already talked about this in some of our other conversations in the context of building the right biopolymers. But in the context of energy, why does running a spark through this apparatus not get us very far?
Yeah, it's very interesting that some people thought that if you just run that Miller-Urey experiment longer and longer, eventually you'd have life instead of just amino acids. And I think that conveys the real misconception that we've been talking about is the lightning, the spark that was applied there. It happened to have been constructive, you might say, to the point of getting to single amino acids, but only because the amino acids were protected then by the apparatus, that they didn't go around and get zapped a lot more after that. In the end, if it were able to produce polypeptides, stringing together amino acids, running those through the spark, I think everybody would admit would be much more destructive than actually progressing towards some kind of a useful protein with a consistent bonding structure to it. So in the end, that kind of experiment, if you just let it run, is going to basically produce junk, tar, just an amalgamation of a whole lot of mess that has no real purpose.
Yeah, that reminds me of Jim Tour's videos recently, where he's talked about the origin of life and some of the challenges in building biomolecules. And the fact that if you look at the protocols for building these molecules in the lab, you need different conditions. You might have to have a different pH, you might need different temperature, you have to have a different amount of time at each step along the process. So if you're just running one step and pouring energy in and you say, aha, I've got some interesting progress, well, for the next step, you might need a different temperature or a different energy source or a different reagent. And so if you just keep pouring the same thing in, this raw energy in the same way, it's just not going to help out in the long run for getting where you need to go.
Yeah, it would be nice to see an admission of that from the Origin of Life community, frankly, that we have to get past even thinking about raw energy ever making useful progress.
Yeah, so talk to us a little bit about that, Rob. How does life harness this energy? How do we convert raw energy into a specific and constructive form that biology can use?
Yeah, it's very helpful, of course, to study how all of life does this. Even the simplest forms of life, we can look at those and say, how do they harness energy? And I find that very helpful. Of course, those who would rebut our message will say life actually started much simpler than that. But we'll get to that rebuttal later, I suppose. But all of life uses, I think you can simplify it to what we call a 3-step process to harness energy and to have it just in the right form when you need it. And an overarching label for that would be chemiosmotic coupling.
Okay, that's a scary word. Why do you need to tell us what that means?
Well, chemiosmotic coupling is a scary word, but I guess if we go into the 3 steps behind the process and break it down, it's not so scary at that point. The first step of it, which is really, I think, well, all of it is genius, but the first step will explain how important it is, how genius it is. But it's basically creating a gradient of protons across the membrane. So the membrane, of course, it could be your cell membrane or it could be a mitochondrial membrane, but it's impermeable to protons. So if you push protons across it, they want to get back, but the membrane won't allow them to get back. So you can build up this gradient. And basically, how it works is you're stripping electrons off of whatever source of food it is. For us, the food is kind of obvious, but in simpler forms of life, the food could even be iron or sulfur or hydrogen gas in simple forms of life. But the process of stripping electrons off of that, and then through a series of precise redox reactions where you're handing the electrons off to some molecule who really wants them, you harness the energy then by pumping protons across this membrane and creating and maintaining this proton gradient.
Yeah, so just for our listeners, Rob, let's back up for a moment on the technical aspect. When we're talking about a proton gradient, what we're talking about is creating a reservoir. You have to imagine something that is enclosed so the protons can stay in there. But you have this reservoir into which the protons are being pumped, like the gas tank I was mentioning on the car. We're pushing protons into there in order to have them available to then do what?
Yeah, so that's a kind of a storage of energy. And then what do you do with that? Well, all across life, you have this fantastically complex nanomachine known as ATP synthase. And ATP synthase crosses the membrane. It's a group of 20 different proteins in the simplest forms of life, like 20 proteins that is resident there in the membrane. And protons who want to get back inside the membrane can only do so by going through the ATP synthase machine. And essentially, it's an electric motor that's powered by the protons wanting to get back in. I guess we're all familiar with electricity, with electrons pushing motors so that they spin. But this is actually protons pushing this motor so that it spins.
So maybe I'm thinking of too many analogies, but I'm thinking of a dam where you've got water on one side that builds up and then rushes through and turns a turbine to produce usable energy. Similarly, as these protons flow across the membrane, they generate actual rotational force, right?
Yeah, I think a hydroelectric dam is a great example. If you think of the protons as water building up behind a hydroelectric dam, and the ATP synthase would then be the energy harnessing part of the dam where the water pushes the turbine and creates electricity. That would be the ATP synthase part.
Right. So ATP synthase is this turbine. It's now rotating. Okay, great. What does that do?
Yeah, so in life, ATP synthase is there to, you could call it recharge batteries. It's basically converting adenosine diphosphate into adenosine triphosphate, or ATP. So ATP is the charged up battery and ADP is the discharged battery. And the process of charging and recharging that battery, so to speak, is going on continuously, very quickly throughout your body in every cell, all day, all the time.
Okay, so this is taking essentially an electric current, turning ATP synthase, which is then producing energy in a chemical form, ATP, adenosine triphosphate, which can then be used throughout the cell. Is that what's going on?
Yeah, and so I had mentioned 3 steps, and so the third step would actually be using that ATP, so having these charged up batteries that are very pervasive throughout your cells. And they are used to run hundreds of different molecular machines or enzymes that do all the processes of replicating or transporting or moving things or repairing things. They all run on the same kind of battery. You can kind of picture a AA battery in your house that can be used for dozens of purposes. That's basically what ATP does in your body.
Yeah, I like that. That's another good analogy. I've always got a bunch of batteries lying around the house. Half the time I'm not sure whether the batteries are new or half used or completely drained. So imagine we had in our house a machine that would round up all the dead batteries lying around the house and recharge them on a constant basis. That would be really awesome. And then we'd have this stream of recharged batteries ready to go, distributed all around the house that we could use for whatever we want.
Yeah, and it's such a convenient and maybe you can even use the word democratized kind of energy source, this ATP. It's all over the place. It can be used for so many different purposes. And the utility of it, the ubiquitous process of it, and it's so convenient for the cell to do so many different things with it. And that's what's so great about the energy harnessing process that's required to get life going and keep it going.
Right. And back to the thing you were mentioning earlier, Rob, we have this raw energy problem where you can't just throw raw energy at a system and expect anything good to come of it. Instead, now we have these little tiny packets available in ATP that are transportable, that last for a certain time frame, so they can be moved around the cell and used at different points in time, all around the cell. And this is important. It's a small packet of energy that can be applied in a very discrete way without destroying the system that it's trying to operate.
Exactly. And all the machines that make use of it are very precisely designed to be constructive, as we've said, and there's not a lot of backfiring that goes on, a lot of destructive mess that goes on in the process. So energy is beautifully harnessed there just the way you want it. It's just the right time for lots of different purposes.
And then these other machines in the cell, and we won't get into that because that's not the purpose of the discussion today, but the different machines in the cell can use this energy to do what? Drive other chemical reactions, convert it back into some type of physical force or physical movement, these different types of processes, right?
Yeah, basically everything that life needs to have done, ATP will be there to do it. Of course, there are other ways that energy can be harnessed as well, but we're trying to keep it simple and keep the focus on the main one, which is ATP.
Right. Okay. Well, this is great for current life and all the complexity that we have today. But just to play devil's advocate, couldn't things have started a lot simpler, Rob? Why do we need all this complexity in something like a simple form of life, like an early bacterium?
Yeah, and that's the question we get a lot. We can dive into some of the examples that have been shown to be simpler or thought to be predecessors to this. I guess I'd like to point out one of the reasons why I think this is foundational and fundamental for all of life. And that is that this will get a little bit technical, but in chemistry, generally you have a reaction of like one molecule comes in and it produces one product, or one molecule comes in and produces two products, right? There's a simple ratio there, and it's called stoichiometric, that kind of ratio. Whereas when we talk about this gradient of protons, it's a little bit more like putting money into the bank.
Mm-hmm.
As we said, putting water behind the dam. So this is kind of mixing metaphors here, but let's say you need to pay your rent. We'll use a financial metaphor here. You have to pay your rent, and your rent is $1,000 a month. Because you have a bank account, you can have income coming in various forms and various sizes, and you can build up money and then pay your rent. I mean, that's what we're all familiar with, obviously. But imagine a scenario where when the rent is due once a month, you have no way of savings and you have to pay the rent immediately. You have to have a source of money that shows up just at the right moment to pay that amount of rent immediately. If you don't have this chemiosmotic coupling, if you don't have this proton gradient, that's what you're stuck with, is you have to have a reaction happen that immediately would have enough energy to produce ATP from ADP right at the spot, just enough energy to do that. And that would be more of stoichiometric chemistry. The genius of the proton gradient is that all kinds of different income sources, you might say, can come and make a contribution and build up this proton gradient. And then when you're ready to make ATP, you can just borrow from the bank, take away from your savings, so to speak, and make ATP as you want to. The real benefit of that is it makes it so robust that all these different sources of income, little pieces of energy that you've collected, can all be put in the bank and put to good use, as opposed to needing just the right amount of money to show up just at the right time to pay the bill that shows up.
Boy, I think you're hitting on something just really profound here. And by the way, it reminds me that people talk about ATP as the energy currency of the cell. So that's a good example you use there. But I think you're hitting on something really foundational here, because if you're relying on a situation in which every time you need something to happen in the cell, you have to just hope that you happen to have the food available, the energy available, the right type of reaction to produce exactly what you need in that exact moment. And then in the next moment, you might need something else. Is this even possible in principle?
Yeah, there is one example in the world of all living organisms. There's something called fermenters.
Mm-hmm.
And so fermenters, through the process of fermentation, they can conduct a very specific kind of reaction, a chemical reaction, which will convert ADP into ATP directly from the reaction. And that's the fancy name there is substrate level phosphorylation. And that is actually a stoichiometric chemistry. It's a 2 to 3 or 1 to 2, I forget, but it's a direct relationship where a direct chemical reaction creates ATP. So that sounds like the shortcut. That sounds like the pathway to get all this started through a gentle process of chemical evolution, right? Well, it turns out that it's kind of the opposite, that because this is such a process that is stoichiometric chemistry, where you have to have just the right reaction at just the right time to make your ATP, much of the energy in that source of food is wasted. It's not very well transferred. It's not very well harnessed. And so you end up after fermentation with an end product that still has a lot of energy left in it that you can't use. And that end product ends up being a kind of a toxin. It builds up over time to the point where these fermenters can no longer continue unless someone cleans up the mess that they've made. And usually that's it has to be some other form of life that actually does use chemiosmotic coupling to clean up the mess. and so fermenters are actually kind of a degenerate form of life, not a pathway of innovation to get to what we have today. I'd also like to mention that because fermenters do this and end up making a lot of mess of products that still have a lot of energy left, but they're more toxic, they actually do need or require ATP synthase. And you might say, why would they have ATP synthase? Because they're already making ATP directly through fermentation. Well, it's fascinating because they actually have to run their ATP synthase in reverse. They actually burn ATP in order to turn the ATP synthase in order to create or maintain the proton gradient.
Interesting.
Running it in reverse. Why do they need to run it in reverse? Well, they need that in order to have membrane transport occur, bringing food in and bringing the waste out. They need that proton gradient for that purpose. And if they didn't have that, they would die pretty quickly. And even with it, they're producing all this toxin that it eventually will stop them from growing or kill them unless someone cleans up the mess.
Very interesting. So they have a critical role, of course, in the larger biosphere in that they take care of the stuff that they're burning, but it sounds like it's not really going where it needs to go in terms of producing an energy currency for the cell that can be utilized for lots of other operations that organisms carry out. Running, jumping, flying, the kinds of things that we need in particular for larger organisms.
Yeah, it's certainly not self-sustaining. And it's kind of interesting when you look at a human that we actually, for moments of time, we can do that as well. If you're exercising and you're exercising so hard that the normal oxygen route to produce your energy is overwhelmed, you're exercising harder than that, you will, for a small period of time, go into a substrate level phosphorylation and you develop lactic acid as your end product. When you're breathless and your muscles start to hurt, that's the lactic acid building up. And of course, we know that can't be sustained. It can help you to make a sprint, and then you got to pay it back.
Yeah, I think the older I get, the shorter my sprints are, Rob. I'm getting breathless pretty quickly these days.
I'm with you.
Well, Rob, this is really valuable. I'd love to have you back to talk more about ATP synthase and this new video about energy harnessing that you and other scientists have put together for us.
Very good. Thank you, Eric. I look forward to it.
Thank you for listening to this episode of ID the Future. To learn more about the origin of life, visit us at our YouTube Discovery Science channel at idthefuture.com or on your favorite podcast app. And as always, consider sharing a link with a friend. For ID the Future, I'm Eric Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.